Hello everyone. So my name is Nicolas Campion. Thanks for calling so many for my PhD defense entitled Power to X and Alternative Fuels for the Maritime Industry. So for my presentation, I will go through this agenda, with starting with a bit of introduction and research guide and research question, then moving to the method and applications, and finally I will present some results and conclusions and recommendations. So let's move with introduction. So a bit of context, as you may have heard of, we have some issue with global warming and climate change caused by greenhouse gases emission, and the energy sector, as we can see in that graph, is the main emitters. So there is a scientific consensus that the cheapest and most efficient way to decarbonize the energy sector is to directly electrify most of it using renewable energy. But some of the sector cannot be directly electrified, and that's our sector that we call the hard-to-abate sectors. One of them that we're going to put the focus on for this PhD is the shipping sector. So shipping is responsible for 3% of the global CO2 emissions. So you can say it's not so much, but it's still as much as the African continent. And if we do nothing, while the other sector will decarbonize, shipping will keep increasing and may take up to 70% of the share by 2050. Also, shipping is interesting because as a hard-to-abate sector, all the methods that will apply for shipping can be applied for other ones, such as iron and steel, aviation, chemicals, and so on. So basically what we're doing for shipping could, with some adaptation, be replicated for larger amount of sectors. So the IMO, the International Maritime Organization, already proposed some pathway for carbon reductions. So one in 2018, not very ambitious, and some in 2033 that are more ambitious. What we'll be looking at in this PhD is the area under the curve. So each scenario is associated with a carbon budget, and then we can see how far it is from what Paris Agreement would recommend. So in this work, in this presentation, I will focus mostly on the 1.5 degrees Alin target, which is more ambitious. Why? Because 1.5 degrees is clearly defined by the IPCC as limits that we shouldn't overlook. And in addition, I've read in Le Monde that if the temperature keep increasing, the wine production in Champagne will be moved from France to England, and we cannot let this happen. So the emissions can be reduced through three different things. So first, design and operational measures identified by the IMO. But as you can see here, we have a green bar that show that without anything else, that we have alternative fuels, we cannot reach net zero. But this other lot of questions. So when we have to change fuels, which fuel should we use? How much do we need? How do we produce them? At what cost? And is it enough to still stay within Paris Agreement? So we're going to address all these questions today. So first one, which fuels? So here we're not starting from nowhere. We're looking at literature and discussion with partners from the project that financed my PhD, MariFuel. We select the existing fuel, so the fossil fuels, the one being mostly used today being heavy fuel oil. We consider blue fuels that are produced similarly to fossil fuels, so basically from natural gas, but coupled with systems that will capture the CO2 emissions and put them underground forever in theory. Then biofuel, second generation biofuel, liquid biogas, for example. And then where the most focus will be is what we call e-fuels and bio-e-fuels. So these fuels are produced in what we call a power-to-X plant. So it looks like this. And I will go a bit more in detail to explain how we produce this fuel. So the main component of the plant, which is important, is the electrolyzer that will split water into hydrogen. So we have different electrolyzer technologies that we've been looking in this PhD. And to split the water into hydrogen, you need some electricity that you can source from the grid, but ideally from renewables to have what we call green or renewable hydrogen. Once you have this hydrogen, you need to transform it to more advanced chemicals that can be used in the ship engines. So you have different ones. The first one we look at with ammonia that you can obtain by mixing hydrogen and nitrogen from the air. e-methanol that you can obtain mixing with CO2. And then finally, bio-e-methanol that use also biomass to produce gas that will be boosted through hydrogen. That's why we have the bio in the title. So now that's all the fuel. If you want to improve the operation of your system, you can also, for example, include the underground hydrogen storage to take account the variability of renewable power. Okay, now let's move into the research gap and questions. So looking at literature about people doing fuel transition pathway for shipping, we can see that it clearly identifies that fuel cost and fuel greenhouse gas emissions as the most important criterion for decisions. But usually these two factors are sourced from different sources in the literature and put in the same model. So this means that you will have a non-fair assumption between the different fuels. So when you compare them, it would be important to have something that get the both together with consistent assumptions. In addition, there is no well-defined and validated method to assess the cost of e-fuels, and neither for joint e-fuel cost and carbon footprint assessment. So this led to our research question. So the first one that we will answer through this PhD, it's what are the possible fuel transition pathways to align the maritime sector cost effectively with the Paris Agreement? And this is lead to also some sub-research question, one related to the fuel cost. So how to estimate the cost for electrolytic hydrogen-based fuels? One to the emission, how to estimate the fuel carbon footprint? And finally, how can we derive fuel transition pathways? Let's move to the method and application to answer this question. So our method will be divided in two main parts. So one part is on deriving fuel transition pathways. So to answer the main research question and research question 3 have been addressed in the paper number 9 and the technical report number 1. And the other part of the method is about finding joint cost and carbon footprint estimates. So here we focus on hydrogen-based fuels. So this part of the method is divided in subcategories that have a logical order. So first, we find a method to get the production cost. Then we adapt this method for every possible fuel production pathways. Then we have also an improvement of the method to include weather-related uncertainties. While we develop these two methods, we also have, in parallel, developing a method to optimally size what we call a power-to-X plant. Finally, we have a part about the validation of the method. And finally, one where we get both cost and carbon footprint assessment. So let's move to the first part. So here, I look at the literature to see how you would traditionally estimate e-fuel cost, back in 2019. One method that you could use for off-grid system is to basically use the SUE, capacity factor, system efficiency, and cost to get the fuel production cost. And if you have a grid-connected system doing more or less similar, but using an average market electricity price or sometimes a low LCOE to get the cost. What is the problem with these methods? So first of all, the plant dynamics and the Hartley variability of the plant is not considered. Second, in general, you usually only consider one source of renewable power source, while having a combination of different, also the grid could be relevant. And finally, you don't consider that the electricity price actually vary hour per hour. So here I come out with the method and the model, which is what we call the linear programming model. So it has been kept linear without including binaries to allow a fast solving of the model. So it has an objective function, which is to minimize the annualized system cost, split in two components, one related to the capacities installed in the system and one related to the operation of the system, like for example, buying electricity. Then we have the main variable that we take decision on, which is the installed capacities and the hourly mass and energy flow for every component of the Power-to-X plant. Then the model is constrained, and the main constraint that we have is, first of all, the yearly production target. That's one that drives the model and forces it to solve. So the plant has to produce a given amount of ammonia per year, or methanol, for example. Then the minimum and maximum load for every unit. And then finally, we have some mass balances that will represent the chemical reaction of the different components and the behavior of storage systems. And then we have the power balances that takes into account the renewable power and balance electrical production consumption in the system. So we have the model. Now we need to populate it with some data to get some meaningful results. So the one we put are the hourly profile data. So we have hourly power profiles from renewable, from wind and solar, for example, and also hourly grid electricity prices. Other data that we need is what we call the techno-economic data. So basically the CapEx, OpEx, and annuities for every plant component, also the efficiencies and the operational constraints. So these can, for example, come from a process model, also from the literature in some cases. And here I would like to add that most of the data used in this thesis have been validated by industrial partners through different projects, so they are quite reliable. And once we have this, the type of result we get, so it's what we want, the fuel production cost for a given production of ammonia per year, then the optimal system sizing, and then the optimal hourly system operation. So if I summarize, the advantage of this method is fast solving on a desktop computer, so less than 30 seconds. It's adapted to run multiple scenarios for different system configurations. It's scalable, so you can include many different technologies. It's free, so from the language to the solver, and it's also documented thanks to David. And then this means that it can help to have reproducible results, which I think it's a useful thing for science. And so as a proof, we'll use this method to very different cases. So here we have the model that can be used, for example, coupled with the ammonia thermodynamic model made by Hossein that has been in paper 1. Also for a bioenzyme synthesis plant model made by René, for example. Then possibly assessment of bio-oils based on experimental measurements made by Antoine with the help of Moritz and supervision of Lasso. Also, we can study the relevance of concentrated solar power for hydrogen production. We did with Jose and Raul. It's also been used for different master and bachelor theses and for various projects and technical reports. Okay, but as good as it sounds, the model is not perfect. So one thing that could be improved is there is only 1 year of renewable profiles that we use to get the system sizing and the costs. So then how do we take in account the uncertainty related to renewable power profile and that the weather is not the same every year? So here we move to the first method improvement, which will include uncertainties. So this we move from the previous model to another one that takes the same input data regarding techno-economics, but instead of taking 1 year of weather profile, you would use 5 that are correlated to each other. Why not more? Because if I take more, it won't solve on a desktop computer, but it becomes too big. The core of the model is then what we call the LP two-stage stochastic model. So this is, you can see the difference in how the objective function is phrased. So basically it will minimize the system costs, not for 1 year, but for all the scenarios. So you have 2 components, what we call the first stage decisions related to the investment, and then the operation stage decisions that are related to that are scenario dependent. Then the main variables are quite similar to previously. So first, the capacities of the system that will be installed. And second, the hourly mass flow. But what changed here is like we have an S that was not there before, meaning that the flows are optimized for every scenario. Then we have the main constraints. So most of them are pretty similar to the previous model, except that they will be applied for every scenario. And then we relaxed also the demand production target to leave the model the possibility to overproduce or underproduce in some scenarios. So this is lead to two more variables, so that over and under productions that are reported in the objective function as an extra cost. And then out of this, you would get the fuel production costs, like we want, ammonia production volume for each scenario, but also the optimal plant sizing, considering the uncertainties of your weather profiles. Another limitation of the model we have, as I said before, to solve fast, they have to be linear. But by doing so, and by not using binaries, you have an operation that is not so detailed. So the question now is, do we still get realistic results? So this is what we look in paper 6 and now. So the method to do that is in the first part, we take the OptiPlant model that I've been presenting. We solve it, and then we get some optimal plant sizing. So here we can use either the deterministic or the two-stage stochastic method. And there's this plant sizing. We call the plant builder. We ask him to build it, and then we'll try in real condition. Unfortunately, I didn't have any PhD budget left to build a plant. So instead, I used the model from my colleague, Ioannis, that has a better representation of the operation of the plant. So it's a MELP model. We give him the sizing from the first model, and then basically we run the model in real conditions for 5 years. And out of this, we get the actual ammonia production volume after 5 years of operation. And then what I call the observed fuel production cost that we can then compare with the previous one to see if we were off or not. Okay, now I presented the method regarding the cost. Now we'll show the one regarding cost and carbon footprint. First of all, I will introduce some few definitions about carbon accounting for shipping. So one is the tank-to-wake emissions. So it's the emission you do by burning and transporting the fuel. Then we have the well-to-tank emissions related to when you produce the fuel. So you have when you build the plant to produce the fuel, when you operate the plant, and when you discard the plant. Altogether, this is called the well-to-wake emissions. In this specific time, I won't look at the tank-to-wake, but mostly at the well-to-tank, as this one will be calculated later on. So I introduce here another notion, which is what we call scope 3 emissions, that will take into account all this, what you see in the red box, and also for the electricity usage, the same. And from this, you would get what we have emission factor related to building the plant, and also related to using the electricity. If I want to summarize, when you use the scope 3 emission factor, you have to account when you build the plant. So basically, the renewable electricity is not zero. Okay, now I take the OptiPlant model, so it's the same as before, and I add the greenhouse gas accounting layer. So this is done post-processing. First, we solve economically, and then we count for the emissions. For that, we need the local grid mix and the emission factors for every component of the plant, and also the grid usage. Then, once you have solved the model, you have the installed capacities and hourly grid electricity consumption on an optimal setup. And from this, you can get what we have, what we call the scope 3 emission of the e-fuel production. So this is great, but I'm not the only one. There is other way of accounting. For example, EU and most of the regulatory bodies They just account for the operational emission, which means that the emission factor of the infrastructure will be zero, and the scope 2 emission will be lower for fossil and zero for renewable power. And this has an influence. It has an influence because, first of all, a regulatory body can influence the way you would do investment and plant operation. For example, you would count the emission of the grid and put some restrictions. So here you take the scope 2 emission factors that have been with the EU accounting method, for example, and you use them to add some regulations that I also can include in the model as additional constraints, for example, to restrain grid usage limit or limit the accounted greenhouse gases emissions. And then, because we also have two ways of accounting, you can get on the first hand the scope 3 emission e-fuel production, but also scope 2, so that would call like sort of legal ones. Okay, now if I move to the next part of the method of the regarding the fuel transition pathways themselves. So we have a mixed integer linear model called CMAPS that has as a variable the number of ships that we would buy and decommission every year, the amount of fuel that we use in every ship, and then a ship stock. Then you will have a driving constraint, which will be to show the transport demand that has to be fulfilled by the shipping fleet. Then we have different constraints related to the fuel usage. So you cannot have as much fuel as you want for your ships because they are limited by availability, for example, due to biomass resources or CO2. You will have to respect your carbon budget aligned with 1.5 degrees. And you cannot produce as many new ships or new fuel every year because there will be some ramping constraints. Then what will fit in the model are different parameters related to the shipping fleet that are cost, the type of fuel that you can use in every engine, transportable lifetime. We'll also model the existing fleet, including orders, and the transport demand. And very important, also the fuel emissions for every fuels and the fuel prices taken from the OptiPlant models that have been presented. Now let's move on some results. So I will organize the results section following the different research questions. So one related to the cost, one to the emissions, and one to the fuel production pathways, fuel transition pathways. So let's move to the first one. So just to explain how we got the results, we've been looking at 3 different sites in the world where you could produce fuels. So good for fuels. So one is in north of Chile, where you have a lot of solar, but not much wind. The other place is a place with a bit more hostile condition with no sun, but a lot of wind. So this is Denmark. And then the last part in Australia, when you have both sun and wind. Then what do you get? So here we have a graph where I show on the dot the fuel production cost, and on the bars, the total annualized cost per category of plant component. So if I take the example of e-methanol, we can see that the large share of the cost will come from using the grid and to having some local solar power. Another large share of the cost will come from the electrolyzer park. So here I choose solid oxide electrolysis because it was the cheapest option, and some part for the fuel plant. Then when you produce methanol, you have an extra cost related to capturing the CO2 that you need in your reaction. And there's also some cost related to the hydrogen storage, batteries, and desalination plant. So then this explains why, for example, ammonia will be cheaper than e-methanol. When we look at bio-e-fuels that use also biomass, you have less cost related to the electricity, but it comes from the biomass. So here it's bamboo based on René Molly. And we can see that it's the cheapest of the 3 options. Still, if we compare to a traditional fossil fuel, here very low sulfur oil, we have a production cost which is still around 3 times higher than the selling price. So there is something to do if you want to bring them on par. So here I've been showing a system that was grid connected and local renewable power supply. What if you just off grid? So if you're just off grid, what will happen? So you remove the grid, but then you have to spend more money on having larger solar park, larger electrolyzer, and also a larger intermediate storage like batteries, so you can keep operating your plant all the time. But in the end, this results to a 9% cost increase using 2030 techno-economic data. In 2020, it would be more around 20%. Now, if I compare the cost I get compared to the other method with the fixed electricity price to see how it changes, we can see that first of all, when you're off-grid, we have solutions that give actually much cheaper cost compared to the one just using LCOE and capacity factor because of the integration between different renewable sources and the use of intermediate storage. For grid connected option, actually, we found pretty similar results when you use the average grid price instead of the hourly one, because the best way to operate your plant is at full load. And then if you use obviously a low electricity price with high capacity factor, you will underestimate your cost by a lot. All right. Another interesting result I got by doing my external stay in the University of Bologna in Italy is that when you use a reanalysis tool like Renewable Ninja, you will actually significantly underestimate your fuel costs compared to using real solar data. So this is to say that all the costs that I will be presenting and using in the CMAPS model later on will be on the optimistic side. Then some conclusion we get about the validation analysis. So when we used our more detailed operation model, is that first, is it fine to actually use one weather years to get the fuel production cost? Well, the answer is yes, as long as the year you choose is an average year, so you avoid the extremely low or high capacity factor. Then is it okay to use a linear program formulation instead of MILP, so a less detailed operation model? The answer is yes. And actually, the other parameters, like for example, discount rates, will have a way bigger influence on the cost estimate than the operational details, especially when you have a hydrogen storage in the plant. And then is it okay to use only one weather use, not for getting cost, but for sizing? Well, the answer is it depends on how much you would manage to sell your ammonia. And then in some cases, the deterministic method will give better results. In some other cases, the stochastic method will give better results. You can read the papers for more details. Now the result related to the emissions of the fuels. So here is what we get after running the model and applying the method I showed previously for different fuels in 2030 in Arica, which is a nice place to produce fuel. It's a lot of sun. So on the bar, you can see the emissions in kilogram of CO2 per gigajoule of fuels. So most of the emissions come from using the grid, and a little bit comes from building the solar plant. Okay, what does this number means? So in black is the scope 3 emissions that takes into account building the plant. And in red is the scope 2, where you don't account for building the plants. So you have lower emission for this. And then how does it compare to fossil fuels? Well, if you take LPG, which is one of the fossil fuels with the lowest CO2 emissions, it's above. So basically you produce a fuel which is 3 times more expensive, but produce more emissions if you use the grid. Except in the case of bio e-fuels, because the biomass count as 0 emissions. So this is because in Chile, we still have a lot of electricity coming from fossil. So basically, if we use the electricity now, if the system doesn't change, it's a bad idea to use grid electricity. And because it's a bad idea, we have to do something. So what we can do is implement regulation to restrain the grid usage. So like EU is proposing or some others. So here I've been looking at different ideas before the regulation from the EU. So one of them is, for example, putting a maximum cap of emissions that you can emit per year. Let's say 30, that's the remainder of the scope 3 and scope 2 emissions. So if you implement a yearly emission threshold of 36 grams of CO2 per kilowatt hour, why is this values? Because it's the one that was proposed by a certification organism called Certify. So here you would get, when you account for scope 2 emission, indeed 36, but then when you account for everything, you go to 70, which is actually close to the emission of the LPG. Here we account for scope 3 for LPG also. Then, for example, you could use the CO2 tax on the electricity. In Chile, we could see that if you put the 100 euros tax, it would work pretty well in reducing the emissions. Another option is to limit the access to the grid. Here, for example, limited to the power unit for the ammonia plant. So here, also good reduction. And finally, going completely off grid, which is by far the most convenient solution, the better solution, even accounting when building the plant. And then what happened is like the cost will increase by going off grid for the reason explained before, but not so much compared to using the grid. So there's something to do here. Later in the model, I will use the emission only from the off-grid fuels and also from the one without restrictions to compare. Now, okay, let's see what fuel transition pathway do we get. So here, okay, I will explain the figure more in details, but this is what fuel production pathway we get in a world we don't have where we don't have much biomass available for shipping, because maybe it's used by the competition or there is not so much sustainable biomass. And then the fuel are produced off-grid, so in a clean way, but a little more expensive. So in this case, what we see, first of all, and this is the yearly emission of CO2 that will decrease to close to zero around 2045, and then doing some not following, for example, the IMO things, but in total, the area under the curve still respects the Paris Agreement objective. So what is this red bars here? Basically, this means that the most DEL did not solve with the fuel option it has and the ramping constraint. So the only way to stay within 1.5 degrees is to reduce the fuel consumption now, while we don't have clean fuels, and the reduction is about 16% of the current fuel consumption. And the reduction has to be sustained between 2026 until 2036 until the green fuel come at scale. Then what we can see as a transition fuel, you would rather use, for example, LPG here rather than heavy fuel oil to limit the emissions now that we still don't have clean fuel available. Then in the long term, you will get some green ammonia, which is the cheapest and doesn't require carbon. In the meantime, we have some sort of transition fuel that are blue ammonia and methanol produced with direct air capture. This is to make sure that we have enough fuel. And I have to add that the assumption that blue ammonia is very sensitive on how you model the efficiency of the carbon capture. Then if I do a little zoom in, actually here there is something, and it's the amount of capacity of electrolysis we have to invest to start the ramping. And this is 5 gigawatt. So what is 5 gigawatt? It's actually a lot because there's 600 megawatt globally installed in 2021. So we have to start now and at scale. For example, Denmark aims to install 6 gigawatt, which is nice, but it's in 2030. If it's in 2026, it's even better. Then if I look at other scenarios, for example, one where the fuel are produced using grid electricity. So we don't control how we produce them. We use the cheapest way, we use the grid as is it today, and we wait that it's decarbonized over time. So here it's even harder for the model to solve, which show that we have a bigger fuel consumption reduction needed in the short term. And then in another world, when we have unlimited supply of biomass, you would rather favor biomass-based fuels like biomethanol, LBG, and refined PO in the beginning, because they are cheaper and on paper with less emissions. Here, emphasize that it has to be a residual sustainable biomass, and that if we cut down more forest, it's not going to work. Then how we can enforce all these things, because they won't magically happen. One way is a market-based measure to reduce the cost between green fuels and fossil fuels. And if we want to use like a CO2 tax to bring this gap closer, you would need a tax, for example, that would go from 50 euros now to 850 euros in 2050. So it's quite a big increase. On top of this, it has to also be combined with fuel consumption reduction. Otherwise, the model doesn't stay below 1.5 degree carbon budget. Now a bit of conclusions based on the whole analysis. So first of all, let's answer to the main research question and give some recommendation. So first of all, which fuel should we use then? So answer is all the fuel should be used in the short term, because we don't have the time and there's a lot of fuels that is used by the shipping, and most likely ammonia in the long term if there is no sustainable biomass available at scale. Then it will be relevant to study a bit more about the role of LPG and other fossil fuels that have lower emissions than heavy fuel oil typically for as transition fuels. Then the fleet should be equipped with a multi-fuel engine that can switch between all the different fuels. And the investments are made now, but they will be useful in the future. It's important to restrain and monitor carefully the grid usage for e-fuel production until the grid is fully decarbonized. Then from 2026, we have to install 5 gigawatts of electrolysis capacities and increase this amount by 50% every year. So that's the same growth rate of PV. And then just to give an idea of the size, if it's 2050, we have to cover all the demand with e-fuels produced by solar. In Chile, we have to use 2.4 times what is today installed worldwide in PV. And that represents covering Denmark with solar panels. Don't note that it's a good idea. Then in parallel, you have to combine this with 16% reduction of expected fuel consumption in the early years while the fuel are not available. So during 2026 and 2035, more or less. And if you want to trigger this change through cost measures, you have to implement a CO2 tax of minimum 400 euro per ton in average, together with sustained and large fuel consumption reduction. So here's a bit of the scientific contribution of this PhD. So with new methods to get the fuel cost and the carbon footprint assessment, method to get fuel transition pathways in line with the Paris Agreement, and then some open access models and some papers and reports. Finally, some perspective, like what science could look like in to improve this type of study. So first, what I would personally like to do is to improve the interface and usability of the tool so it can be used by others than only researchers, or also other researchers, and have impact on society and improve the reproducibility of results and validation. Then one thing that would be nice is to actually validate the cost and carbon footprint estimates on the real power-to-X plant. And then we could expand the analysis to other hard-to-abate sector, so not focusing on shipping, but also of shipping, aviation, chemicals, and so on. And then one thing that could be interesting to look at is like we've been only looking at CO2, but there's a lot of other things that we don't want to damage, like land use. Do we have enough materials to produce all these green fuels solar PV, wind turbines, batteries, and so on. And if it can affect biodiversity, typically to have all these very large plants all over the world. And then finally, what would be nice is to see if the slides here would apply in real life. So that's what we can start doing because we are late already. Thank you, everyone.